So Sungyong recently got his PhD in 2020 from USC, and his expertise is quite unique, right? He is extremely motivated and passionate about something that is emerging as physics-based, physics-inspired machine learning. And I would like to invite Sungyong on the stage to introduce the motivation of his work as well as his various discoveries along the way. Thank you for being here with us.
Hello everyone. My name is Sungyong Seo, and I'm currently working in Google Cloud AI. And it's a great opportunity for me to see many people whose interest is what I'm interested in. And then thanks for the introduction. So today I'm going to talk about my work, which was presented last year New Lips conference. So I'm just afraid that my talk is going to be slightly more like academic-wise presentation, but I hope that you guys are not overwhelmed by some formula or mathematical things. Yeah. So I got my PhD 2 years ago, and then as he introduced me, my thesis is more likely about how to incorporate the domain knowledge with the data-driven learning. And I believe that this kind of direction is a bit unique because many people have thought that the data-driven learning is kind of dominating, and which is working very well across many different domains, such as the computer vision, natural language processing. But still, during my PhD, I was believing that maybe there's another way we can utilize the domain knowledge to make the data-driven model better. So anyway, so let me start my presentation. So the the main title is the controlling neural networks with the rule representations. Okay, so over the last decade, as I just mentioned, that many people believe that we can learn the latent representation from deep learning by just feeding high quality and large scale label data as many as possible. And this direction is actually very working well across the many different domains, including the computer vision and natural language processing. But still, there are many other fields where the prior knowledge, domain knowledge, or rule is very essential. So such as the heuristical reasoning for fraud detection, or equations such as the physics-based equations for physical modeling, or some associative logic to understand some logical thinking, or others. So I believe that still using the domain knowledge or rule-based learning seems effective if we do it very well. Then why do I claim the learning with rules? So I believe that the prior knowledge has to improve the test accuracy in problems with the minimal supervision with extra information. And actually, this is related to what Dr. Wan presented in this morning's keynote. So we are not able to wait to collect many data from many failure in the practical application, or it is already good to apply the knowledge with data-driven model to make the model more better accuracy. And another thing is that we can improve the trust of the deep neural networks by reducing the inconsistent predictions. So the people may think that the deep learning can provide very accurate prediction, but still domain experts think that, or domain people think that if their output is not following their rule 100%, it may block them to use the deep learning model because they don't understand what's going on inside. And then last is that we can improve the robustness of the deep neural networks. So the constrain the model searching space, reduce the sensitivity to the slight changes in input, which is going to make the model more robust and durable. So, but the rule is not only enough. So rule itself is helpful for understanding tasks in many domains still, but we need one more feature called the controllability, because even when a rule is known to hold the 100% of the time, we are not sure how much this rule contribute during the running, or sometimes some rules are only partially informative, so their contribution should be carefully adjusted. Therefore, we need a framework in which we can control the rules contributions or data's contributions. Ideally, this controllability should be enabled at inference without the need of retraining or fine-tuning. So conventionally, this is the loss function when we define the when we use train the deep neural networks. The L task is usually say the loss function for the objective task. So for example, classification, we need to reduce this classification error as much as possible. Or if the task is a regression, then this loss form is something like mean squared error, so that we want to minimize this loss term as much as possible. And additionally, we add additional constraints, so-called loss rule. And then we are going to define this lambda, which is the rule contribution or rule weight. But this conventional approach has some limitations. So first of all, we need to define the lambda before the training. So usually we do the cross-validation to find the lambda value, so that we need to do the cross-validation, define the lambda, and then let's pick up the lambda for the whole training. So it means that the model is going to be static after trained. And then this lambda is not adaptable to target data at inference. So during training, actually this lambda is coming from the training data itself. So when we actually deploy our model to the real application, maybe this lambda is correct, but maybe this lambda is not correct. So we want to adjust the rule dependency, but there's no way to change the lambda after training. And then the third one is that due to the deep learning's updating rule, this rule is supposed to be differentiable. But as you know that in the real world, rules may not be simply or easily differentiable. So in this work, we proposed this structure, so-called deep controllable neural networks or deep control. And then as you can see, we have the X and we have the output Y. And as you can see, the Y hat is the prediction of our neural networks. And then depending on task, we want to make this Y hat as close as much as possible to the labeled Y. And then what we proposed in this work is that we feed this X into the two passages. One is the rule encoder and another one is the data encoder. And it can be any types of the neural networks. It can be MLP, CNN, RNN, depending on your task or data. And then what we get from rule encoder is a ZR, and ZD is from data encoder. And then we believe that the ZR is the latent representation for rule, and then ZD is the latent representation for data. Then how we teach the data encoder and rule encoder to return the proper ZR and ZD. So the ZR is coupled with the loss function, specifically L rule, and then ZD is coupled with the L task, and then in this way. So we sampled alpha from the predefined distribution P, and then alpha's range is from 0 to 1, so that if alpha is 0, it means that we are going to ignore the L rule for training, so that this neural network is going to be used only the data encoder. If the alpha is 1, then we are going to ignore the data part, and then we are only going to use the rule part to get this task. So during the training, we are going to sample many different alpha, so that to make the rule encoder is going to learn rule dependency as well as some kind of task dependency, because the L task contribution is going to float not only the data encoder and rule encoder if the alpha is some value between 0 and 1. So another advantages of this deep control is that once the training, still we are able to control the alpha depending on your task or your target. So once the model is trained, when you feed the X, actually we can define the alpha by yourself. So we can set the alpha 0.5, something like that. that we can get the some kind of the intermediate decision between the rule and data. As I mentioned in the previous slide, another limitation the conventional method is that the L rule is supposed to be the differentiable, but here we propose the way to incorporate the non-differentiable rule into our frame. So I'm not going to cover very details, but we actually added the perturbation idea so that we can add some small displacement to the X input, and then we are going to get some relation between the perturbed input and perturbed output with the original input and original output. So depending on your rule, we can also open the gate that to incorporate the non-differentiable rules. So we are going to cover the 3 use cases, including the improving the reliability given prior knowledge on the physics simulation. And another one is the examining the candidate rules, whether this rule is informative on target or not. And then the third one is that the domain adaptation. So after training the model, we are going to apply this trained model to the different target just by adjusting the controllable parameter. So improve the reliability given rule. So basically the task is the predicting the next state of the double pendulum system with the friction. So as you can see, there are 4-dimensional input and output. So basically where these 2 objects are located and what was their speed at time t. And then as you can see, since this is a regression task, I define the L task as like the mean squared error. But additionally, I add another rule-based constraint, which is called the energy damping rule. Since this friction, since there are friction on these 2 objects, as time goes by, their movement is going to be stopped eventually, and then their energy, combining the potential and kinetic energy, going to be 0. So I don't know whether this figure is clear to you, but as you can see, this is the mean absolute error, which means that how much we can predict the next state as close as possible. And then its MA shows that if we use the task with the fixed lambda, and if we increase the lambda, we can see that we can reduce this error quite much. But the thing is that, as I mentioned in the previous slide, it is hard to predefine lambda before spending many times for training. And then the verification ratio is that how much the predicted output is violating or following the rule we defined. So it means that if the 0 verification from some baseline, it means that their prediction is completely violating the energy damping law. But if their verification ratio is close to 1, that means that their prediction is completely following the energy damping law. So physicists may think that the prediction from the neural network or any other model should follow the energy damping law, because this is kind of the very, very solid ground truth. And as well as we want to minimize this error as much as possible. But without spending much time training, by using the deep control, we can control the alpha to find the optimal point. And then this point, we can see that the verification ratio is pretty large. So compared to other baseline, what we achieved is that we don't actually spend many times for finding the proper lambda before starting training, and by just one-time training. And after that, we can just control the alpha to find the better position of the model. And then the second use case is the examining the candidate rules. So here we show that the deep control is able to do the hypothesis testing for rule. So the task is that we are going to predict how much a certain item is sold in a given time span. We got this data from Walmart, and then here we applied some common rule between the price and sales. So the rule is that the sales rule is that if the price is decreased, then sales is going to be increased. So there is the negative correlation between the delta prices and delta sales. I know that the old items are not following this rule. Maybe some items are not oppositely following this rule, or some items are following this rule. And then we are going to see how much this deep control is able to figure out whether this rule is correct or not. So for our experiment, we first split the data, items, into the 3 groups, so-called negative 0.1, 0.2, and 0.3. So the 0.1, 2, 3 indicated the negative correlation coefficient, so that the items in this group shows here like a slight negative correlation between the price and sales. But the items in negative 0.3 follow the rule we defined more strongly than items in these 2 groups. And then as you can see, after training, we can see that the optimal alpha located in 0.2 meaning that our rule is a bit is kind of helpful, but it's not very dominating. But as you can see in this graph, the alpha is located in 0.9, which means that our rule is more effective to describe the items in this group. So from this experiment, what you can say is that we can actually quantify how much this rule is important, or how much this rule is less important, something like that. So overall, the deep control enables user to examine how much the candidate rules are informative. So if we can see get this kind of figure, we can say that our rule is pretty valid for this target. But if we can see this figure, maybe we can say that our rule is not somehow effective, but not very efficient, or not very helpful to understand this data. And then another case I want to show is this slide. So as you can see, there is another 2 groups saying positive 0.2 and positive 0.3. And as you can guess, the items in positive 0.2 means that their price and the correlation between the price and sales are actually positive. So more expensive, more sales. And then items in this group, positive 0.3, has shown that the stronger positive correlation. So it means that these items in these 2 groups are not completely following the rules, so that this rule is actually harmful. So, and then as you can see, after training on negative 0.2, when we apply our model to 0.2, positive 0.2 and 0.3, we can see that the best alpha is located at 0, which means that the rule we actually incorporate for training is not very necessary or not very helpful. So from this, we can quantify that again. We can quantify that whether this rule is good or not. And then the last case is the domain adaptation. So the task is that the cardiovascular classification. So we have some set of the features, and then the task is that we are going to see whether a patient has the cardiovascular disease or not. And then the rule we incorporate here is that higher blood pressure is known to be, higher blood pressure is affecting the higher chance of the cardiovascular disease. Maybe this is true, but maybe this is not true for all the patient. So we split the patient into 2 groups, the unusual groups and user groups. And the user groups is that a patient having the higher blood pressure with the cardiovascular disease, or having a low blood pressure and no disease. And the unusual groups are opposite. And then source, as you can see, we mixed up the patient to define 4 different groups: source, target 1, 2, 3. And as you can see, the source ratio, you can see there are the majority of the patients are from the unusual group. And then as you can see, target 1, 2, 3, the majority of the patients are from user or same, the ratio is same or unusual. So we trained the deep control model on source first, and we are going to apply this source to target 1, 2, 3 in this figure. And as you can see the source figure, you can see that this is the classification error. It means lower is better. And then as you can see, since the rule is opposite to the unusual group, so that the alpha is located in the very small number. But when after training the source data and applied to the target 1, you can see that the best alpha is going to be higher than before. And it means that this group is following the rule we incorporate during the training. And actually this is the same, as the ratio. And then from target 2 to target 3, we can see that the best alpha is moved from 1 to some intermediate value between 0 and 1. And this is kind of the expected behavior. So overall, we believe that the learning from rules helps construct interpretable, robust, and reliable deep neural networks. And then the deep control is the model architecture, data type, and rule type agnostic. So it can cover any types of the data, any types of the rule for your purpose. And then enables the controllability of rule strength at inference without retraining. This is another unique feature of the deep control. So we also propose the perturbation-based rule encoding to support the non-differentiable rule into the data-driven model. And then we verified our idea over the 3 different use cases, like improving reliability, examining the candidate rules, and domain adaptations. Okay, thanks for paying attention to my talk. And thank you. Yeah.
As a practice AI engineer, myself, I have to thank you a lot because you touched on so many pain points that we have observed doing the job. Right? In the past, where we want to train the loss function of anything, you include a tiny parameter, you hit run, and then you wait 5-6 days and see the model coming out and test whether you like it or not. Right?
Yeah.
And I've heard there are even parameter setting committees that convene every few months and say, okay, what parameters we want to try out this quarter, right? And, so this is actually very very novel, and I believe it's going to be very important for certain tasks that need this kind of information. So the floor is open for Q&A.
I'm wondering at what scale you think rules would be most useful in terms of like a data set. If you take a data set from like a smaller, more concentrated area, the data you get will probably differ from another area, like geographically, for instance.
Yeah, this question is kind of the like very practical question. So I won't say that the answer is depending on what's your task and what your data look like. So for example, in my last user case is like a cardiovascular classification case. As you can see, the data size, we cannot say that it's very large data set. So since the task is pretty simple, but if the task is going to be harder and harder, like associated with the images or natural language, something like that, then the number of data required to get the safe training without rule, or the number of data requiring the rule is going to be very dependent on how much was your task. But generally saying that, I think that the computer vision or natural language processing have already provided pre-trained model on a lot of the large amount of the corpus, so that I'm not sure whether rule is really impactful for those kind of the applications. But in industrial AI, such as the predicting the anomaly behavior in the next future, something like that, maybe since our data point is not that many, so maybe in that field, the rule is more helpful or more beneficial.
To what extent do you think a framework like this could be used for like transfer learning? Or if you had a factory or a Walmart in one place, then you had sensors and data and measurements, and then you had a Walmart somewhere else and you didn't have it, but you had the same rule set, could you still make inference predictions complementing the lack of data with the symbolic side of?
Yeah, this is also another practical question. So here in the domain adaptation task, we, as you can see here, to show the capability of our deep control model, we intentionally split the data to follow or to easily show our performance, but it doesn't say that it is easy. It's not always working in the real application. So, for example, in some other applications, maybe even though they have the two similar tasks, maybe it's hard to transfer between A to B or between B to A because there some other aspects are different. So I want to say that this work is kind of open the gate that this is one way to incorporate rule, which is human understandable, with the data-driven model, but still there are a lot of challenges or blockers we need to figure out how to make it really practical solution in the industrial AI field.
So we have maybe I have two questions regarding to the model, the loss function you have. Because I can see that the loss function you have the L, it's equal to L plus lambda of the L rule, for example. So is there an assumption in this case is a convex function to converse the optimal control?
You mean is there any assumption on whether loss function itself? This value is...
Yeah, that's combined with rule and...
So we don't have the assumption that the L rule or L task are supposed to be the convex function, but this form itself is if the L rule and L task are given, then this term, this combination is the convex term. So we don't, I won't say that we don't have any specific constraint on the L rule and L task. So actually there is some, actually this is a good point. So as you may expect that the scale of L rule and L task can be very, very different. So for example, L rule is something like a 10-ish scale, but the L task is going to be 0.00 some scale. So that in the case, this simple alpha and 1 minus alpha is not very effective. We need to think about maybe normalization or some other techniques to make it work. But generally, we don't have any assumption of that behind whether those two values are convex.
But in general case, in assumption, you have many rules. For example, if you put it, I have a paper regarding to, I have many rules. This is all the physical parameter. But when I encode it and then learn the loss, it converts, but the rule disappears altogether.
Okay.
So I'm curious, how can you resolve this case? For example, when you adjust, although it convex, although it converts, provided convex or not converts, but it's disarray on the rule. So how can you adjust the
so yeah, I see. So for our experiment, we only assume that there's only a single rule we want to incorporate, but if the number of rules are increased, like multiple rules are simultaneously incorporated, I think that those cases maybe we need to think about. But for this experiment, we haven't seen kind of the things you described just. So I don't have the So
which means that you will be sitting next to each other during lunch, and then I will accidentally sit nearby.
Yeah, maybe I can get some more context from you to get the answer. Yeah.
Any last question for Sungyong? If not, then